So I promise I will get back to galaxy evolution. It seems like a weird way to get into it, but I'll explain the connection as it comes up. So I've been working on the host galaxies of tidal disruption events. So we think that we're seeing these kind of events when a star passes close enough to a black hole that the tidal forces then from that supermassive black hole are enough to overcome the self-gravity of the star, tearing it apart. So this is predicted to occur such that we'd see it as long as the black hole is less massive than about 10 to the 8 solar masses. So for most galaxies in our local universe, the black hole should be small enough that we should be seeing these kinds of events. So recently there's been a number of claims of detections of this kind of event. So let me just show you an example to show you what we're looking at when we think that we're seeing this kind of claim. So this is an example from 2012 by Tidal of PS110JH, which you don't have to remember the phone number, but this is kind of like a prototypical TDE that was bright in the UV optical. So this is the spectrum of the event itself. So you can see it's very blue. And then if you add a galaxy stellar continuum to a black body, here this is about 30,000 Kelvin, you see that there's these residual broad helium lines in the spectrum. And so between these broad helium lines, the very blue continuum, and the time evolution, so here I'm showing the detection of this event over the course of about a year in various different bands, and you see that it has this characteristic rise, and then the fall-off is about 10⁻⁵, which is consistent with what you'd expect from the mass accretion onto the black hole. So this is kind of a template event. We've been looking for more and more events in other surveys. So in things like PTF and now IPTF, Assassin, as well as some other time-domain surveys, we've been looking for events like this to try to see if we can find more candidate tidal disruption events. So this is what Yair Akavi did. He went through the PTF archive, as well as some other claims of tidal disruption events, and tried to find things with this similar broad helium, occasionally hydrogen lines. So these are some of the events that he found. So this is the one that I just showed you, with this broad helium line. And then he found some others that seem to also have maybe a broad H alpha line, in addition to the helium line. These are shown with the continuum suppression off, that's why they're so flat. But with this, we were able to come up with a sample then of UV optical bright TDEs that we're pretty sure are really TDEs. With these unique features, we can be pretty sure that these aren't some kind of weird supernova. And then going back into archives of, especially the PTF events, able to potentially rule out recurring AGN activity. Certainly there's a number of other claimed TDEs in the literature. These are all bright in the UV optical, but there's a number that have been bright in the X-ray. Some of those are better sampled than others, and I'll get back to one of them that's especially well sampled. But for now, I'm just going to focus on the ones that have this particular signature, since we can kind of think of them as a class. They have this thing in common, and whatever they are, they're probably all the same thing.
Tucker, quick question. These are single star events?
Yes. Yeah, probably. Some of them it's not clear, like if the whole star was disrupted. Some of them might have been just a small part of the star, something like that. But yeah. All right. So for the class of TDEs like this, Yair Akavi had plotted some spectra of the host galaxies. And so this is what the host galaxy spectra now, not of the event itself, but just of the galaxy, either way before the event or way after, look like. And this isn't really a normal, like you just picked 9 random galaxies, you wouldn't expect to see a class like this. So there's only one star from a galaxy here. Some of them kind of look early type, and a lot of them have these very strong Balmer absorption lines. So especially these top two, you can see here that this H epsilon added into the calcium line makes it stronger than the other calcium line, and it's kind of a indicator that the Balmer absorption is very, very strong. So this is weird, and we wanted to quantify how weird this was. Are the TDEs going off in galaxies that are somehow unusual? So Anna and I had been studying this kind of galaxy with very strong Balmer absorption, like these ones, and little emission from current star formation for other reasons related to galaxy evolution. And so we got in contact with Yair, and we wanted to quantify these kinds of galaxies. So this is a plot that we usually use to quantify and find post-Starburst galaxies. On the y-axis, I'm showing the H alpha emission, which is indicative of current star formation. And here I'm plotting all the galaxies with spectra from Sloan. And here I'm showing the H delta absorption. And so this is kind of a different duration star formation tracer. If this is tracing current star formation, this is tracing star formation over the past few years or so. So you can see some familiar features in this plot. This is kind of the blue cloud of star-forming galaxies that are forming stars now, and they have been for a while, at least the past year. And then over here we have kind of the red sequence of early type galaxies that are currently quiescent, and they haven't had star formation within the past few years. They've been quiescent for a while. And then when we try to find galaxies that are post-starburst, that have had a recent starburst that's now ended, we look here in this region. So we want to find galaxies that have little current star formation, but had a ton of recent star formation in the past few years. So finding these kind of galaxies is interesting for studying how galaxies evolve, but it also happens to be where we find a lot of the TDE hosts then. So here's what we found looking at the host galaxies of the events that I just showed you. The red ones seem to be very clustered than the bottom right of this diagram. To give you a sense of how unusual this is, this rectangle here is only containing about 0.2% of the Sloan population. And then extending this to get 3 more of the TDE hosts, that's only 2% of the rest of the galaxies. So somehow, most of the TDEs are occurring in this very rare class of galaxy. You can really only get to this kind of spur of this diagram with a burst of star formation. So that's what I'm showing you these lines here. These 2 darker blue lines are showing what happens if you have various bursts that last 1 to 200 megayears added onto an old stellar population, and then you kind of go through here. Kind of a slow decline in the star formation would give you something like this line here. So this light blue line is showing what happens if star formation declines over about a 3 gig-year time scale. You see you have a little bit of enhanced Balmer absorption compared to the normal galaxies, but you don't quite get to the spur. These galaxies really seem like they must have experienced some kind of recent burst in their recent histories, at least in the past year. I mentioned that most of these were these UV optical bright events. There's one event that had good enough host galaxy spectra that was detected actually in X-ray, and X-ray gamma ray bright, this one. There's only a few events that were well characterized in this way. This is the one that had these 2 lines in the host galaxy spectra that we could find, and it's here. So even this one higher energy event also seems like it has this low current star formation, but maybe a recent burst. All right, so this really begs the question of why. Right? Why should a TDE, why should a star in the center of its galaxy about to be destructed by the black hole care anything about the recent global properties of the galaxy? The timescales are just that different. Yeah, so I didn't mention because of the rarities of these kind of events, the TDE rate has to be much higher, factors of 30 to 200, depending on how you slice up this diagram. So what this implies for the rates, theory predicts that we should see about a few per 10,000 years per galaxy. And in the post-starburst, we're finding about that, maybe even higher, maybe 1 per 1,000 years per galaxy. But then the rates in normal galaxies, which had previously been experiencing some tension with theory, are now much lower. So in the normal galaxies, we're actually not finding many of these TDEs. So now there's about a factor of 100 of a discrepancy between the rates that seem to be observed in normal galaxies and the rates that seem to be observed that are predicted then from the theory. So is it possible that there are selection effects that are causing this effect of what we're seeing? So we shouldn't be selecting against TDEs in normal galaxies. Normal early type or star-forming galaxies have about the same amount of dust, perhaps as the post-starbursts. They should have about the same amount of dust down to the nucleus as normal early types. So we really shouldn't be selecting against normal galaxies. However, I'll get to in a second reasons that we think might be causing this effect. Anything that could possibly cause this effect might also be happening in starbursting or Euler galaxies or galaxies with strong AGN. And in those cases, we probably would have missed a TDE. So there could be a large number of TDEs in starburst or AGN galaxies that we've missed, either because there's substantial dust obscuration of the event, or because in finding these events, we've been selecting against galaxies with past AGN activity. And so it would be really hard to disentangle that effect from the TDE. All right, so what could be causing this effect? Well, in looking at post-Starburst galaxies kind of for their own sake, a lot of them look kind of like this. This is a really pretty example. It has this big tidal tail. About half of them, when you look deep enough, seem to show these extended tidal and shell features. They really seem like they're a product of a major merger, with the idea being that the major merger triggers a starburst, and we're looking at it a few megayears to a gigayear afterwards. So if these are galaxies that had a recent major merger, we might expect that the supermassive black hole binary that forms could increase the TDE rate. So if each of these galaxies has its own supermassive black hole, then the galaxies merge. The supermassive black holes will also go through this period of in-spiral. And three-body interactions in between the two black holes and a star that comes in could definitely enhance the TDE rate. Let's see. During the starburst, we know that the gas tends to be funneled to the center, creating very essentially concentrated bursts of young stars. So maybe it's possible that just the amount of stars that have a potentially center-crossing orbits is just enough that the TDE rate is boosted to explain what we see. Another possibility is that if we're seeing kind of a sweet spot of stellar evolution, where a few hundred megayears after the starburst, we're seeing very easily disrupted stars tend to dominate and might be more easily disrupted. That could explain what we're seeing. Another possibility is that the TDE rate is enhanced by circumnuclear gas. I'll get back to this in a little bit, but the post-Starburst galaxies tend to have liner-like spectra, so indicating that perhaps it's related to the circumnuclear gas. But it's not clear that you could boost the rate as much as we need just by this effect alone. All right, so to start to address these, we wanted to look back at this diagram. So we think that we're seeing more enhancement at stronger H delta Balmer absorption than we are at weaker Balmer absorption. So what causes galaxies to kind of move along this track? So unfortunately, there's a number of possibilities. Galaxies here could be older than these, or they could have had weaker starbursts, as in a lower amount of mass was formed, or they could have had longer duration starbursts, such that mass that was formed over a longer period of time. And so with just these two quantities alone, we can't tell the difference between any of these. We can't tell the difference between an older starburst or a weaker starburst. So we need to use stellar population fitting on these galaxies to disentangle all these effects. So we do this for the TDE host galaxies with the idea that if there was a central concentration of stars, we might see that the TDE host had especially strong starbursts. Or if the TDE enhancement were related to the evolved stars, we might expect to see maybe a narrow range of post-starburst ages. And this is what we found. So here I'm showing the age that we've measured since the starburst ended in these host galaxies. This one is still forming stars. It gets a negative age since the starburst ended. The starburst isn't ended. Don't give too much weight to exactly what this value is. We're kind of ignoring it for now. And then here I'm showing the fraction of mass that was produced in the recent period of star formation divided the total. So here we see that most of the TDE hosts have formed a few percent, maybe 10% of their current stellar mass in the recent burst. And this is not that much. A lot of the post-starbursts that we see, that we detect for the purposes of studying galaxy evolution, have formed maybe something like 30% of their current stellar mass in the burst, but only a 1% burst is really not that substantial. Other thing we found that's not plotted here, kind of the third axis, is the duration of that period of recent star formation. We're finding that most of them have very short duration starbursts, indicating that we're not seeing these galaxies after a decline, kind of a long decline in the star formation history. We're really seeing them after a burst. And we also see a wide range of post-burst ages. Ignoring the one that's still forming stars, for the ones that are currently present, we're seeing them maybe 100 megayears to a gigayear after the burst has ended, meaning that whatever has enhanced the TDE rate either operates over a long period of time, over a gigayear, or has a lot of variability in when it can act. So we need a burst. And then if what we needed to boost the TDE rate was a large number of stars, we really can't explain that with the starburst. What we need is a very high concentration of that 1% of the new stars, if this is what's explaining the effect. It doesn't seem like we're looking at a very sweet spot of evolved star evolution, given the wide range in post-burst ages that we're finding. All right, so there's one galaxy that's a post-starburst that had archival HST images that Stone and Van Pelsen went and looked at to see if the central concentration of the galaxy was enough to explain the rates that we're seeing. Basically, is it just cuspy enough that there's enough stars in that last cone that could have this large, this high rate of TDEs? And they found that they expected a TDE rate in this post-starburst of about 1 per 1,000 years per galaxy, which is consistent with what we estimated from the comparison with the Sloan spectra. So in at least one case, it's possible that a high central concentration of stars formed in the recent burst could increase the TDE rate enough. All right, so the other possibility relates to if they're recently post-merger. And these are the images from Sloan of the 8 host galaxies. And it's really hard to tell if they're post-merger, right? Are there merger signatures? Are there like shells? It's really, really hard to tell from the Sloan images. Like this one is kind of barely even there. So as kind of an alternative argument, we wanted to look at this age since now instead of when the servers ended, I'm looking at the age the servers began as a way of getting a proxy since the merger coalesced. So the idea being that for major mergers, you can go from that coalescence to, you can have those galaxies coalesce very quickly. But for a minor merger, the time for that smaller galaxy to decay in through dynamical friction will be very long. So by constraining the time since that coalescence, we can try to constrain the possible mass ratios of that merger. So essentially, because these ages are so short, because they're in general less than a gigayear, it's unlikely that we found galaxies that were post-minor merger with that minor merger ratio being less equal than about 12 to 1, which makes kind of intuitive sense. If we're looking at them just after the merger, that merger can have taken a lot of time to occur. So they're probably relatively equal mass, the two components, if what we're seeing is really post-merger. Why is this important? Well, in the real universe, we expect that there should be a lot more minor mergers than major mergers. And theory predicts that the TDE rate, the total number of TDEs that you'd get should be fairly insensitive to that mass ratio. So the fact that we're seeing most of these to be post-major merger, if they're post-merger, means that the fact that we have the two supermassive black holes in a binary might not be what's causing this. However, this depends really sensitively on the exact model that you use. And so this is still kind of an open possibility. All right, so I mentioned the circumnuclear gas. So here I'm showing galaxies from Sloan on the BBT diagram. So N2 over H alpha and O3 over H beta. So you have the star-forming galaxies and then Sieverts and Liners. So galaxies with similar quiescent, Balmer-Strong spectra tend to be here. So most of them are in the Lionel-like region. Some of them are Sieverts-like. And then in these crosses, I'm showing the TDE hosts. So a lot of them, there's this one star-forming galaxy again, and the rest of them tend to be either Sieverts or Liners, consistent with the other galaxies like them with respect to their star formation histories. So does this mean that they're circumnuclear gas? Well, not necessarily. For the post-Starburst galaxies, we've been looking at this with GMOS to try to get a handle on what the spatial resolution is of the emission lines. Because there's a few other possibilities besides a low luminosity AGN that could cause this ionization. So one of them is merger shocks, which if most of these are post-merger, we would expect that these emission line ratios should have these high ionization states spread out over the galaxy. Similarly, post-AGB stars can mimic this signature. And again, we would expect to see this linear-like signature spread out over the galaxy in the post-Starburst if that was the case. So this is something that we're investigating for post-Starburst in general, now also for these TDE hosts, to try to see what the real ionization source is. And we see a similar picture here for this Venn diagram. So N2 over H alpha again, with the H alpha equivalent width instead. Most of the TDE hosts are then in this liner-like region where they don't have very strong emission lines, but they do have this non-star formation like ionization. All right, so here's kind of a picture now of the possibilities. It seems like the supermassive black hole binary can really only work if the TDE rates are most enhanced for a major merger. It's possible in at least one case that the central concentration of stars is enough to explain the rate that we're seeing. It's unlikely that the evolved stars that we're seeing like a sweet spot in stellar evolution to explain this, and whether it's related to circumnuclear gas is still kind of unknown. So to keep going and try to address these possibilities for good, we've been undergoing a campaign with HST to get images of the host galaxies, so to do better than the Sloan images that I showed you, to see if they do show signs of a recent merger. And then we've been we're getting images of nearby analogs, so galaxies where we haven't seen a TDE go off, but they're close enough that we can really map that central concentration and see if they're cosmic enough to explain the TDE rate. Then we've been getting cis spectra on 4 of the known hosts to try to resolve where the ionization is coming from, to try to constrain what the ionization source is, to see if there's a low luminosity AGN in these galaxies. Right, so with that, I'll conclude. So we've been looking at tidal disruption events. They seem to occur at a rate that's much, much higher, almost 200 times, in these rare post-Starburst galaxies. Stellar population fitting reveals that there's a large range of ages after the starburst, where we see TDEs, and that this increase in rate might be driven by a central concentration of new stars, but there's still a lot that we hope to do with the new HST data at the end of this year and next year. So I'll take questions. Thanks.